So we'll start. We'll start. We'll start. We'll start. We'll start.
To you. My voice is audible to you. Video also. Fine, then fine. Okay, right.
Okay.
Oh, good. Good, good.
Good morning, all. On behalf of management, Principal Dr. G. Apparao Naidu, Dr. T. Srinivasulu, HOD of BSH, I, V. Susan Shalini, invite all the participants for the participation of the webinar. A webinar topic is dielectrical materials and their characterization studies in the microwave frequency region. Okay, let us brief about Vigyans. Vigyan Institute of Management and Technology for Women is the brainchild of the Dr. L. Rataya Garu, Chairman, Vigyan Group of Institute. And was founded during August in 2008 with the 4 branches of engineering. VNTW is an explanatory institute of higher learning with the mission of pursuing excellence in education and research. The institute, with their diverse and dynamic community of about 2,000 students, offer a distinctive combination of different graduates program, EC, CSE, IT, accomplished faculty, world-class facilities with hostel and with this greenery. Vigyan's vision to empower students with a professional education using a creative and innovative technical practice of global competency and research aptitude to become a competitive engineers with ethical values and entrepreneurial skills, and mission to impart a value-based professional education through creative and innovative teaching learning process to face the global challenges of the new era to inculcate research and to bring out a creativity in students and teachers by imparting engineering knowledge, embodying interpersonal skills to promote innovative research and entrepreneurship. So it's a great, immense pleasure to introduce today's speaker, Dr. Vishwam, an associate professor of physics, GITAM University, Hyderabad campus. Sir, our objective is like towards a wider knowledge and understanding of the basic scientific facts, and to have a teaching profession as his career, and would focus towards implementing new and challenging ideas in many scientific researches and teaching methodologies. Dr. T. Vishwam has completed his Ph.D. In IIT Madras and MSc Applied Electronics, a university second topper, Shaddan College of Studies, Hyderabad, Osmania University, Telangana State. And the areas of research interest like microwave dielectrical studies of hydrogen bond liquids, quantum chemistry and molecular polarizability calculations and liquid crystals. And regarding the projects and publications like international and national journals around 37 under review, and proceedings of international and national conferences are around 6, international conferences are around 12, and national conferences and workshops are around 20 plus. And the achievements which Sir has been the Best Teacher Award, 40 under 40 theme, South India's Inspiring Young Teachers, the New India Express Index of 3rd June 2017. And the next award is SPA Award of Excellence, FDP, on use of ICT in education for online and blending learning conducted by IIT Bombay, 2nd May to 10th July 2016, and chosen as an associate faculty for the faculty development program, and a best paper and poster awarded in national seminar, and best student award for college first in BSc 1999, and best poet award Telugu in BSc 1999. So it's a great pleasure to introduce today's speaker, sir.
Yeah, fine.
Okay.
Is it
So,
audible? Is it audible?
yes, sir, it's clear. It's
Yes, fine.
audible, sir.
Okay.
So, like as you have mentioned in your achievements, like you have a like best poet award in Telugu in 1999.
Yeah, fine.
Okay. So, like any one quotation at the end of the webinar, can we listen from you? Any poetic? Yeah.
Let's see. Let's see.
Okay, it's great, sir. Wonderful, sir. So, like, you can take over, sir.
Okay, fine. Yeah. So, good morning, all. So, madam introduced me. So, I'm only faculty. Don't feel that I don't know anything. I'm a lifelong learner. So, whatever the difficulties I've faced during my PhD program, measurement techniques, I'll share with you. So, this is only the sharing the knowledge. So, whatever the ideas I have, so I can share with you. So, what are the practical difficulty levels in a measurement of materials? I'll share with you. Okay. So my brief profile is I done PhD under the guidance of Professor V.F.K. Mutigaru and Professor V. Subramanian. So I done my studies in dielectrics of liquids, but I'm having complete idea about how to measure the dielectric constant of solid materials and liquid materials and liquid crystals, the different frequency ranges. I use almost all the techniques for characterization of dielectric permittivity in the microwave frequency region. After my completion of PhD program, I have moved to Fiji IIT JE coaching center. Then afterwards, I'm joined in GITAM University I'm working in GITAM University from last 10 years. So during the entire process, I'm still connected with the research. My teaching is the first and research is the second priority. I'm making 50-50. So I'm doing the both teaching and as well as the research process. I have done collaboration work with the Central University of Hyderabad. I'm now presently associated with Professor K.C. James Raju. There I'm doing all the micro measurements using broadband dielectric spectrometer, which in the frequency range 10 microhertz to the 20 megahertz region. And also I'm using the vector network analyzer from 20 megahertz region to the 67 gigahertz region. So I know the techniques. I'll share with you whatever learn. I'll show some of the animation how you can understand the things properly. So this is about my the activity. So I'll start my lesson presentation now. If you have any doubts regarding my presentations, if you have any doubts, I've given my email ID, so you can contact me at any time. I'll also share my WhatsApp number so that you can contact me regarding this. Is it fine for you, everyone? My PPT is my PPT is visible to you, everyone.
Yes, sir.
Okay, fine. Okay, so I'll start now. My today's topic is dielectric materials and their characterization studies in the microwave frequency region. So my lecture talk I arranged in this manner because some of the people are new about the dielectric materials. First, I'll introduce about the fundamentals of dielectric materials. In that, I'll talk about what they mean by dipole moment, how they're categorized, what type of polarizability exists in the material, how the polarizability depends on frequency, how it is depend with respect to the temperature, why I'm specific about micro frequencies compared to the infrared and other radiation techniques, what are the parameters we can estimate from the electric materials. So I'll ask one of the question to you, which is interesting. So you can think of and give me the answer later. This is about the first part. I'll take about 20 minutes to explain the fundamentals. The next part, I'll cover with frequency characterization in a different frequency region, from static frequency region to the microwave frequency region. Once we get the data, once I'll get the data in a different frequency region, so how the relaxation plots will be plotted. Yeah, please. Please, can you mute your mic, please? Can you mute your mic, please? So, how the frequency, the electric measurement from static range to the microwave frequency region. Once you get the data from the microwave frequency region, what are the properties you can study? Example, everyone interested about the relaxation time, how it can be calculated using different models. The next part is why I'm interested about only the biological liquids, what are the importance, and some of the published results I will discuss with you. Then summary and acknowledgement. The first part and second part is a crucial. Those who are in the beginning of the research career. So how it can be characterized, where the facilities are available, I'll discuss with you. Come to the first point. So the materials can be categorized into three parts: solids, conductors, and insulators. I'm speaking about the insulators. On the insulators, we can say that it doesn't allow the flow of current. So the insulators in that category is the dielectrics. So what is the difference between the insulators and dielectrics is the dielectrics materials consist of bound charges compared to the insulators. These bound charges are going to be response with respect to applied field. So with respect to that point, the dielectrics are insulators, but all the insulators are not dielectric materials. I'm repeating once again, dielectrics are insulators, but all the insulators are not dielectric materials. Example, if you consider wood is an insulator, but it's not a dielectric. If you take the Teflon is a dielectric and an insulator. So like this, suppose we take the glass is the dielectric and also is insulator. So like this we can categorize. So they are poor conductors of electricity. Means the conductivity of dielectric materials, if you consider water, it's in the range of 10 to the power of minus 4 to 10 to the power of minus 2 Siemens per meter. So this is the conductivity of dielectric materials. So due to the bound charges, so what happens? It constitutes an electrical dipole moment. So what do you mean by electrical dipole means? Two equal and opposite charges separated by a small distance. This is said to be the electric dipole moment. So this dipole moment, if how many dielectric in the material, how they're responding with respect to the electric field, that matters. Can you mute your mic, please? I request the participants, please mute your mic. So the dipole moment can be defined as it is a vector quantity, two equal and opposite charges separated by a small distance. This is a distance is nothing but a vector we have to consider from the origin. The unit of dipole moment is the debye, which is the CGS unit. Here, how the dipoles are responding with respect to the applied field that makes an important configuration in the microwave. That is the reason the dipole moment is the microscopic variable. This microscopic variable responding for the macroscopic variables. I repeat, these dipoles are responsible for the any properties like dielectric constant or polarization. These are the macroscopic variables. If you look at figure, when electromagnetic waves propagating through the different materials, how they behave. If you go for conductor, if you please can you mute your mic, please? I request, please mute your mic. So in the case of a conductor, the electromagnetic wave get reflected. Why it get reflected also we'll discuss now. So when electromagnetic wave is propagating through a dielectric, pure dielectric, how it behaves, if it is going through the water medium, how it is behaves. So these are the things I'll explain first 20 minutes. So based on the dipole moments, the materials can be classified into three categories. One is permanent dipole moment. If we consider a water molecule, which is an asymmetrical structure, so due to the asymmetrical structure, it constitutes an dipole moment. So these type of materials are said to be the permanent dipole moment. Example, alcohols, proteins, these are all the things related to the permanent dipole moment. Even our body also contains of more number of amino acids, which constitutes a dipole moment. So these dipole moments are how they're relaxing with respect to the frequency region is more important. Similarly, what do you mean by induced dipole moment? The meaning itself induced, that means we have to force. By giving certain amount of electric field, this bound charges displaced by smaller amount constitutes a dipole that is said to be the induced dipole moment. If you consider a quartz material, by the symmetry, the quartz structure is SiO2 hexagonal structure. So with this symmetry, the dipole moment is zero. But when you apply the pressure, what happens? There is a change of the symmetry that constitutes a dipole that is said to be the induced dipole moment. The next part is a temporary dipole moment. So especially in the polymers, with respect to the dispersion mechanism, they exhibit certain dipole moment that is said to be the temporary dipole moment, which occurs in the case of dispersion mechanism. When you disperse the polymers in different materials, and with respect to the frequency range, they will exhibit some dipole moment. That dipole moment is called temporary dipole moment. The major focus on the permanent dipole moment and induced dipole moment. So some of the researchers were working in the case of polymer materials. Please look into the case of a temporary dipole moment. When the polymers are dispersed in a different medium, and we want to study the frequency properties, at the time you experience this dipole moment. The next parameter is a polarization. So if you consider a material, there are n number of dipoles. How the dipoles are aligned in a material. So when you apply certain amount of electric field, there is a torque is acting on the dipole. So due to the torque, tau is equal to P cross E. So they're trying to orient in the direction of applied electrical field. That means there is a propagation of electric field through the material. How much amount of electric field is propagating through the material is said to be the susceptance. The meaning of susceptance is to access the electric field lines through the material. So with respect to susceptibility, the polarization can be defined as how many number of dipoles are oriented in the direction of applied field. How many number of dipoles are oriented with respect to the applied field per unit volume. That is said to be the polarization. The polarization is a vector quantity and it is a macroscopic variable. This macroscopic variable depends upon the dipoles. The dipole is nothing but microscopic. So here the 2 points we have to understand. The polarization, susceptibility, these are the macroscopic variables which depends on the microscopic variables, dipole moment and polarizability. The polarizability, if you consider a single dipole, so that is said to be the polarizability. The small p is equal to alpha into electric field. Alpha is said to be the polarizability. Now, how much amount of electric field is propagating through the material is said to be the susceptance. So the susceptance related to the dielectric constant. The dielectric constant is the intrinsic property of the material. The dielectric constant is the intrinsic property of the material. It can be measured by capacitance in a liquid medium to the capacitance in the air medium. So in general, we know that what is the use of dielectric materials. In the case of capacitor plates, if you insert the dielectric material, the charges are induced. The capacitance is equal to Q by V. If more number of charges appearing on the capacitor plate due to the inserting dielectric medium, so due to that, there is a storage of electrical energy can be increased. So especially in the battery point of view, we need a suitable dielectric constant material of higher dielectric constant so that the storage capacitance can be increased. So if we understand this particular figure, without dielectric, what is the electric field? With the dielectric, what is the electric field? What is the induced polarizability? I can say the induced local field within the material that also matters. The net electric field in the capacitor plate is due to the free electric field and also the opposite electric field. What is the net polarization? So with respect to that relation, if you calculate, the E local field, if you look at any standard textbook in a solid state physics, you'll find the definition local electric field. The local electric field can be defined as the field which is exists inside the dielectric material in the presence of electric field. That is said to be the local field. With respect to that condition, the polarizability, how it depends, how the dielectric constant related to the polarizability, these are the two factors plays an important role in the microwave frequency region. The polarizability and dielectric constant, how they're responding with respect to the frequency. I repeat once again, in the dielectric constant, in the microwave frequency region, I'm interested about the dielectric permittivity, polarization, polarizability. These are the factors and depends on the frequency and temperature. This is the one. What I'm discussing about the Clausius-Mozarti equation. This is the equation which relates the microscopic variable to the microscopic variable. I repeat, alpha is the microscopic variable, whereas dielectric constant is the macroscopic variable. So these are the things that are related. If this dielectric constant depends on alpha, polarizability, this polarizability depends on dipole moment. So this is the relation between this. The dipoles are oriented, alpha will be greater. If alpha will be greater, susceptible will be greater. If the susceptibility is greater, dielectric constant is greater. So these are the things related with respect to the sequence. If we come from microscopic to the macroscopic, like A, B, C, D. Finally, the D depends upon A. So this alpha depends upon the dipole moment. That dipole depends upon alpha. Alpha depends upon epsilon. So these are the sequential parameters. Let me analyze one of the graph. So the same thing, I've taken the capacitive plate. What is going to be happen? When the alternating magnetic, alternating electric field is propagating. So like this, there is no change. If in between this, I'm keeping a dielectric slab, what is going to be happen? When introducing the dielectric slab, you see the difference compared to this and this. There is a phase change. Look at this. This is set to the wavelength, beta, wavelength lambda. Beta is equal to 2 pi by lambda. That is a phase change. There is a phase change. This is a non-polar because the non-polar material does not contain any dipole, so that there is no absorption. If an electromagnetic wave is propagating through the polar medium, a water or Teflon or anything, what happens? The energy get decreased. Why energy get decreased? That energy is taken by the dipoles. These dipoles are doing some work. So due to that phenomena, the energy absorbance will occur. So this is the relation. I hope you are following this. The next part is what sometimes I'm calling as a dielectric constants, sometimes I'm calling as a permittivity. There is a difference. Simple example I will tell you. We call resistance. We call impedance. When you call resistance, when you call impedance, the resistance is nothing but when you're dealing with the static DC voltages, we're calling as a resistance. If this material is suspected, if the material you're passing in alternating fields, then you're going to arrive reactance. That reactance may be due to the inductance, that reactance may be due to the capacitance. So in that case, we are not calling as a resistance. We're calling as resistance plus reactance. So this reactance depends upon the frequency. I request the people please mute yourself. So this is the one. So there is a phase lag between the applied voltage and the polarization that constitutes an the complexity that makes complex. So in the complex phenomena, there is a phase lag between the voltage and current or electric field that responsible for the reactance or this point. The reactance may be positive, voltage leads the current, or current leads the voltage in the case of capacitor. So that makes a complex. So when you call static, dielectric constant, when you call alternating frequency, I'm calling as a permittivity. The permittivity is a complex value. It consists of real part, it consists of imaginary part. This real part tells about the storage of electrical energy, whereas this imaginary part tells about the dielectric loss. The meaning of dielectric loss is there is a phase lag between the voltage and current. So due to that, what happens? The energy get absorbed. That is said to be the dielectric loss in the material. This dielectric loss is responsible for the heating in the material. I'll demonstrate what is the working principle of microwave heating. So in the case of non-polar, so you not get the second part, you will get only first part. In the case of water material or polar material, you'll get the dielectric loss. Here one thing you have to observe, why I'm keeping minus sign. This is not you can keep plus also. Why I kept minus sign? Because of there is an energy loss. The loss in general, we are please can you mute your mic?
I request
I
the
request
participants kindly please mute the mute the mic. I
most
request the
of the
participants kindly to mute the.
okay fine. So
Yes, sorry
in
for that.
general, no problem. In general, it happens, no problem. And because we are in the offline mode, right? Doing
Yes, sir.
online,
Yes.
we can't say that in a house even also face a problem. My kids are playing. I can't say no because they are doing their work. We are doing our work. Okay,
Yes, sir.
it happens. It happens. Our job is to do in the office, not at home, right? We can't have the right
Yes,
to.
sir.
Yes, it happens. No problem. Okay, fine.
Uh,
So here, the minus sign shows loss. If anything is plus, that means something you're getting, you're calling as a plus. Something is lost, you're representing minus. In the same manner, we are representing a negative sign. The negative sign represents loss. I'll tell you one of the example. So in the case of optical materials, there is an emission. In the case of optical materials, there is an emission. So in that case, I can say the refractive index. Generally, we know that only refractive index is a positive value. But when you go for alternating frequencies, time varying fields, there is also possibility of complexity. So due to that, the refractive index is an absorption and emission. In the case of optical materials, we're representing plus. This is the convention. So generally we may confuse with why we are keeping minus sign, why we are keeping plus sign. This is the difference between that. It is the absorption, this is the emission. So this is what you have to understand from this. So especially in the microwave frequency region, when electromagnetic wave is propagating through a polar medium, certain amount of energy gets absorbed. That is responsible for the microwave heating. So this is what the first part with respect to static. When the material, dielectric material, is suspended to the alternating electric field, time varying fields, then these dipoles behave in a peculiar way. Let me say that the dipole may be vibrate, the dipole may be rotate, and there is a internal change of structure. These are all the things leads to the dipole moment. The dipole moment may be categorized by rotation. There is one possibility. The other rotation mechanism, otherwise a vibration, otherwise internal displacement of a nucleus and electron cloud. That also constitutes a dipole moment. So that is the reason the alpha, the polarizability is due to three factors. Generally, there's one more polarizability, space charge polarizability, which occurs in the low frequency region. Those who are dealing with the semiconducting materials, they're dealing with only the low frequency region. At that point, you may arise space charge polarizability. This space charge polarizability is due to the diffusion of ions into one side to the other sides. That may cause space charge polarizability. The next part is dipolar. The meaning itself indicates dipoles. Then this dipoles is rotating, means there is a torque is acting on the dipole. There is a torque which is acting on the dipole. That torque rotates the dipole in flip one direction to other direction. Now here the point is, what do you mean by relaxation? So people may confuse about what do you mean by relaxation. The relaxation is what is the time taken to move from one equilibrium position to the other equilibrium position. What is the time it has taken to move from one equilibrium position to the other equilibrium position? That is said to be the relaxation. This relaxation time is so much important for especially for the biological point of view, because they possess different relaxation mechanism at different frequency region. That relaxation mechanism is used to develop a biosensors. I'll explain at the end. The next one is ionic polarizability. The ionic polarizability is nothing but there is a vibration. Let's consider one example. Take a spring which is connected to certain mass. The mass is suspended. Hold it some time. Pull the mass into downward direction. Release it. What happens? The spring starts vibrating. The result, spring starts vibrating due to the stretching force F is equal to minus kx. The same way here also, this plus and positive nucleus and electron cloud, this also starts vibrating. This vibration polarizability is said to be the ionic polarizability. The vibration polarizability is said to be the ionic polarizability. It is associated with respect to the inertia. It is associated with the inertia, nothing but mass of the ions. The next part is electronic polarizability. The electronic polarizability is nothing but which occurs in the optical frequency region. The frequency is so high so that there is a displacement of the positive electron cloud that constitutes a dipole moment. That is with the electronic polarizability. Among all the three polarizabilities, first one depends on frequency. Ionic polarizability also depends on frequency. The electronic polarizability also depends on frequency. But one important factor in the case of polarizability is only one polarizability depends on temperature. That is said to be the dipolar polarizability. I'm more specific about dipolar polarizability because it depends on frequency, it depends on temperature. I repeat once again, this dipolar polarizability depends on frequency and depends on temperature. Simple example, with respect to this equation, let us confirm 2 points. The first point is, as a temperature is increased, polarization is decreased because they are inversely proportional. As a temperature increase, the polarization decrease. Once there is a decrease in polarizability, the dielectric constant value also decrease. As a temperature increase, polarization decrease, the dielectric constant is decrease. First point. The second point, that E is nothing but electric field. E is nothing but electric field. That electric field is a time varying electric field. So as the frequency is increasing, the dielectric constant value is decreasing. So these are the 2 points you have to understand with respect to the dipolar polarizability. So this is a graph generally observed. Based on this graph, we have to say which is a polar, which is a non-polar. The polar materials, the dielectric constant value decreases with increase in temperature. I repeat, the dielectric constant value decreases with increase in temperature, and also for non-polar materials there is no change. For non-polar materials, there is no change. So by using this graph, we can say which is the polar and which is the non-polar material. The next part. I request the audience to mute your mic, please. I request the audience, please mute your mic. I request the audience, please mute your mic.
Hello? We can still hear the TV volume. Can you please kindly switch off? I request the participants, please kindly unmute. Sir, we can't hear your voice, sir. Sir? Sir, we can't hear your voice, sir. Maybe you're in the mute button, sir.
Check, ma'am. Hello?
Hello, sir. Yes, sir.
It's okay, ma'am. It's okay, ma'am.
Yes, sir. Yes, sir. Now we can hear.
PPT is visible to you?
Yes, sir. It is visible.
PPT is visible to you?
Yes, sir.
Ma'am, can please control the mute, ma'am.
Yes, sir. We will do it. We will take
No.
this.
You're fine.
Thank you, sir.
No. I request the participant, please mute your mic. It disturbs my concentration. Can I continue now? Madam, can I continue?
Yes, sir. Yes, sir. Kindly, you can continue.
Yeah. Why the metals reflects electromagnetic waves? So look at the anything. This is the general question you encounter in the teaching life. Why these metals reflects electromagnetic waves? How they're associated? This is the one. Otherwise, you may get the question in the classroom. Why the electromagnetic waves get reflected from the ionosphere? This is the reason behind for that. Why the electromagnetic waves get reflected from the ionosphere? This is what I'm trying to do this. Otherwise,
So the screen
you can do a
we
small
can increase,
experiment
sir.
right here.
Sorry to disturb you. The screen slow. Can we increase the presentation?
Yes, ma'am. Is it okay now? You're fine? Because it is a fixed mode. Okay, don't worry.
Okay, sir. Done, sir. Okay, sir. Yeah, now it's better, sir.
Yeah, fine. Yeah, do one thing.
Very clear, sir. It's very clear.
It's very clear. Okay, yeah, fine. So to make this a practical issue, do a small homework at your house and you can demonstrate in the classroom also. Take your mobile phone, put it in a steel box, steel container, a tiffin box. Take your mobile phone, switch on the on mode only, keep it in the tiffin box, steel, metal, and close that. Now try to make a call. Try to make a call. What the information, what message you'll get out of coverage area. You'll get the information out of coverage area. You can do demonstrate in the classroom this experiment. The same experiment what you do, Take a plastic box, keep your mobile phone in there, try to make a call. You'll get that the phone gets ringing. What is the button? What is the thing is happening? And then this and this. The first case, electromagnetic waves are propagating. The second case, electromagnetic. The second case, the second case, in the second case, electromagnets will get reflected. You can do one more thing. Put the water, fill the plastic tray into water, complete water. Keep your mobile phone near to that. At that time you will get your signal. At that time you feel that the signal strength is very less. Why? Because something is happening. One case, electromagnets will get reflected. The second case, perfect signal. In the third case, something goes wrong. What is happening here? This is what I'm trying to discuss. So here we're dealing with the plasma frequency. We're dealing with the plasma frequency. So you can know about what is a plasma. A plasma is nothing but four state of matter, which is the ionized form. We have four state of matter: solid, liquid, gases. The fourth one is a plasma. This is the ionized state. All the ions will be in the ionized state. So they're having some vibrational frequency. Your incoming frequency, nothing at electromagnetic wave. Let me say this energy level is even, which is lesser than the plasma energy. What happens? It gets reflected. So that is the reason, due to the plasma frequency, the energy level of the electromagnetic wave, which is very less. So due to that, it gets reflected back. Whereas if energy level for X-rays and gamma rays is greater compared to the microwaves, so due to that, it can penetrate. So this is the logic behind to understand the plasma frequency, why the metals reflects an electromagnetic wave. I repeat, this plasma frequency is responsible for the reflectance concept. If you look at closely with respect to this relation, the reflectivity is a matters. In the case of this, the n value, the refractive index value is 0 in the first case. So due to that, it becomes 1. Whereas in the case of higher frequency, the energy is greater than the plasma frequency, it can penetrate. So that is the reason all our electromagnetic waves get reflected from the ionic state, fourth state of matter, which is energy is very less. Whereas in the case of X-rays or gamma rays, the transmittance is so high so that it can penetrate through the material, it can penetrate through any one of that. So that is the reason the microwave is nothing but non-radiation concept, whereas X-rays and gamma rays are something but radiation. The non-radiation does not get harmed, whereas the ionized radiation, like a particles, wave nature, that may get harmful for you. So that is the reason the microwave radiation is usable for the cooking of the food, whereas non-radiation does not. So this is the concept for that. Why I'm dealing this? If the person who is doing the dispersion studies of any clay materials, at that time your dielectric absorption power is going to be so high. Why it is so high? Because of this concept. So this is the frequency dependence curve of dielectric constant with respect to the frequency. Just now I said, as the frequency increases, the dielectric constant value is decreasing. Now, the permittivity is also the part. The microwave oven is designed based on this graph only. This water molecules absorbs more electromagnetic energy at one particular frequency, that is set with the resonance, the microwave resonance. So due to that phenomena, the microwave is designed. The microwave invention is a sudden accident. It voluntarily is not discovered. It is a sudden accident. The person who behind the microwave oven is an electrical engineer. His name is Percy Spencer. When he's working in a company called Raytheon Industry, he is designing for magnetron devices in the World War II. At that time, he kept a pocket. He kept a chocolate in his pocket. When he's operating this magnetron, which is a source for microwave, he observed that this chocolate got melted. He doesn't know why this got melted. He's so curious. Next, he also concerned, okay, this is something related. So finally, he did with number of materials. He concluded that, okay, water material, which is a polar material, is responding. So the microwave is connected with the polar material. So this is the way the microwave energy is, microwave oven is discovered. You also feel the same thing, right? If you speak mobile continuously for longer time, your ear surface area get heated up. Why it is get heated up? If you take the radio waves, it's not get heated up. Why this microwave only is affecting us? Because our body contains polar material. The polar material nothing but water. These water molecules are responding that particular radiation. So due to that, the heating is taking place. Okay. I'm concerned about only the microwave frequency region. Now you got the doubt. Sir, microwaves. Micro is nothing but -6. Why it is called microwave? Because the wavelength associated with the microwave is in terms of millimeters region. The wavelength associated with the microwave is a millimeter region, and the frequency associated is 10 to the power of 9. So that is the reason we call it a gigahertz waves or microwaves. In general, we are calling as a microwave, where we are designed with respect to the wavelength region. That is the reason it's a microwave. Now, let us look at this microwave. When electromagnetic wave is propagating through the material, these water molecules are trying to rotate. The friction between the dipoles causes heating. The friction between the dipoles got it heating. So this phenomena is said to be the dielectric heating. I think I'll ask one question to you because we are using microwave at home. Can you try keeping oil? Take a cup of oil and place it on that. Is going to be cooked? If you take oil in a cup and place it in the microwave oven and operate for 30 seconds or 1 minute, is it going to be heated up? No. Why? Because oil is a non-polar. Otherwise, we are keeping any food in the ceramic plate. We are taking food in a ceramic plate and keeping on that. The food get heated, whereas ceramic plate is not get heated. Why? Because ceramic is a non-polar which doesn't respond. The polar materials only get respond. So this is the working principle of microwave oven. So I'll ask one question to you. Can we cook egg in microwave oven? The answer is no. I think some of the people get tested. Your microwave oven got completely spoiled because of this bursting nature. So let us try now. I'm demonstrating one experiment in front of you. Let's see the video for this. I kept egg in a microwave oven. See carefully. Within 2 seconds, it got bursted. I repeat once again. What is happening here? Because it's a very good concept. If you try to understand why it got bursted, you are going to be very good. You're very sound in physics. Look at this. What is happening here? Don't try. If you try it, you're gone. Your microwave is completely, you have to clean 2 times with the Surf Excel or Lysol. Okay. You can try with water, you can try with open, anything, the same feeling. If you put in water, it will take 1 second extra, nothing else. The oil contented food cannot be cooked in the microwave oven. And also, why we are not able to keep any metal objects? Because of reflectivity is so high. The electrical charge is the electrical charge which is coming from the sharp edges that may give a short circuit. The electrical charge really leaked from the sharp edges that is responsible for the damage of the microwave oven. So these are the fundamentals related to the microwaves. Now let us discuss about the second concept, how to characterize in the frequency mode. So in the frequency, I'm starting with the zero frequency that is set to be the static. So here I want to measure the dielectric constant. Most of the engineering colleges we are measuring the dielectric constant of liquid sample. This is the liquid holder. It is nothing but a cylindrical capacitance. One is hollow cylinder, other one is the thick cylinder. In between the two cylinders, we are keeping a non-polar material, a liquid. What is the capacitance in the without liquid? What is the capacitance with the liquid? So that will do the dielectric constant of the liquid. It is works only for non-polar. It is works only for non-polar materials, but not water. If you keep water, what happens? The polarizability for the water is greater. That is the reason it does not give perfect value. It gives tolerate. The capacitance for water is so higher, so does not give. We can't measure the dielectric constant of a water. The next part is the one more method. This is also same method which is available in the day-to-day life or physics laboratory. This is the beaker. Inside the material, you want to keep this and vary this length, vary this column length. It is also capacitance. Two cylinders will be there. In between the cylinder, the liquid will goes up like two parallel plate capacitors by a small distance that measure the capacitance. So by using this mechanism also, we can measure the liquids. But suppose you want to measure the solid sample. Some of the people are working in the ceramics, some of the people are working in some materials. How the dielectric constant be measured? The same instrument can be used to measure the dielectric constant at that one frequency is static, zero value, zero frequency. What we have to do is there are two capacitor plates. In between the capacitors, we have to insert the material. Here, this is the cylindrical capacitance. What you have to do is you have to make the diameter of the sample properly. It may be a round pellet. Then you have to find the thickness, and that sample should be have more density. Density is the electric constant depends upon the density also. You have to make the proper density of the sample, then you measure it, you'll get the correct value. I've seen most of the practical difficulties. The people are making the powder, they're taking the powder, they are making pressing, then without density, they're measuring the dielectric constant, which is not correct. What we have to do is, once you make the powder into the pellet form, then fire it, go for sintering process, then we get the more density. Means all the molecules or atoms, they're going to become together, the density of the sample is increased, then measure the dielectric constant. Without density, if you're measuring the dielectric constant, which is we can't report. This is the static. Suppose I want to go for a frequency region, LCR. Generally, we're calling as a LCZ meter. So Z is nothing but resistance plus impedance. In this meter, the same procedure. This is the where you have to insert the. See, look at this. One person kept a sample here with respect to this metallic plates. They connected to the machine. Here, LCZ meter, it typically works for range. It have different frequency ranges. 100 hertz, 120 hertz, 1 kilohertz, 10 kilohertz, 100 kilohertz. Generally, for the ceramic people, those working in the ceramics, ferroelectric materials, they'll prefer the LCZ meter to characterize this. They use this one. So, with respect to this dielectric LCZ meter, you may get the impedance Z prime, Z double prime. You from that you can calculate the dielectric constant, dielectric loss. You want to calculate the low frequency conductivity, you can use it. Like the number of parameters you can get from this particular instrument. There are quite a number of good papers are available. The major point here it is, once you get the impedance data, you have to calculate density versus dielectric constant. There is a provision that you can calculate the temperature of this also. By varying the temperature also, from low temperature region to the above room temperature, maybe it can go up to 300 degrees centigrade. Depends upon the purpose. You can measure the dielectric constant with respect to the temperature, with respect to the frequency, how the parameters, the relaxation time is going to be changes. So there are a number of relaxation models are available in the research field. Maybe the I can say that the Vox Magner conductivity formula, all these things are available. This is one. Suppose this is the major important point. Suppose they want to go for less than that frequency. From I want to measure the dielectric constant for microhertz region. There is a facilities available at University of Physics, University Grants Commission Knowledge Resource Center. This is open facility, so we can do the measurement here. This is the broadband dielectric spectrometer, which is provided by the Novo Control Technologies. For any details, please visit this site. Here, we are going from 10 microhertz region to the 20 megahertz region. We can vary. This is the sample holder. This is nothing but a capacitor. There are two metal capacitors where you can insert the sample here. So this is similar to the LCZ. This range for hertz region. This is comes of 10 microhertz region. It's coming from very low level, 10 minus 6 to the megahertz region. We'll get very good data. So we can interpret the what is happening to the lower frequency regions, what is the conductivity. Nowadays, everyone looking for this particular frequency region for more number of applications. So this is a sample. We have to keep the sample here. We have to load it here. This is the place we have to insert this complete holder into this. That should be placed with respect to the temperature. You will get lot data in this 10 microhertz region, 20 megahertz region. We can keep the span frequency. We can keep number of frequencies from one end to other end. We may get 1,000 points. If you interpret the data, you're going to get very good published results. The major practical difference here for this particular using this one, if at all you want to go for lower steps, with this it may take half an hour to take the data. Suppose you want to continue for a large number of data points with the temperature variation, you have to load the sample holder here. You have to wait for at least 3-4 days to get one sample data for all the frequency ranges and the temperature ranges. This is the one. And also a little bit costlier. This is a highly sophisticated instrument. Once you get the data, so you can interpret the results of the different mechanisms, like in the Johnson, the dielectric relaxation of solids, referred by Johnston. All the relaxation models can be fitted using this particular software provided by this company. It's not a free software; it's an inbuilt software where we can use. The next, suppose I want to measure polymer samples. Those are working in the field of polymers. This is a holder they can use. This holder consists of everything works on the capacitance model only, but you have to keep one drop of polymer liquid in this area. You have to drop one single drop of polymer liquid. It may be dispersion or anything. You can mix anything. Keep it here on this particular topic, this particular layer, and close it and place here. In this one, keep one drop of liquid in this. This is a seal for that. This is sample holder for the liquid sample. Keep it one drop, which this particular surface having a higher surface tension. If you keep any liquid, it does not pour it out. It is going to stick together. So like this, seal this complete holder, then keep it in the place of solids. Remove this and insert and keep it in this. So like this, you can measure the 10 microhertz region to the 20 megahertz region. The people who are working in the area of polymers, dispersion studies, or biological tissues or proteins, they can use this method. You'll get a lot of relaxation mechanisms in this region. The one more is that the polymer samples or maybe liquid samples. This is called interdigited electrode material. This is nothing but a chip. Our observing that this is the a coated one, metallic coated one. Here, you're keeping one drop of liquid in this. You keep one drop of liquid, 1 ml of liquid here. It stick to that. So, in the place of, there is one more facility here. That like how you're inserting a SIM card. The same way you can insert this chip in the particular holder, the same holder, so that you can measure once again the dielectric permittivity for this particular frequency region. The major disadvantage for this particular is this one is cost around $150. This chip consists of $150. It can usable only for 1 or 2 times, but not lifelong. Whereas this sample holder we can use for multiple times. We can use it for multiple times. No, this one we have to throw it out because the liquid is going to sit into the pores of the material, so we cannot use it. It is used only for 1 or 2. So this method for polymer samples, a liquid sample you can use. Suppose you want to measure the solid sample, you can use this particular setup. This facility is available at University of Hyderabad, so you can work it out. So this is about the low frequency region. The next part is the microwave frequency region. In this part, there are 3 techniques are available: transmission line method, cavity method, and open probe method. Nowadays, we are preferring this particular method. I'll tell you the facts about this, but the difference of this and this and this. Especially, we are all engineering colleges. In engineering department, you may have this X-band setup, microwave transmission line waveguide method. So by using that mechanism also, you can measure the dielectric permittivity of that frequency. Let me demonstrate this. This is the setup they are using in the engineering colleges. This is the complete setup. This is the power supply. Klystron is a microwave source. This is the isolator, which isolates the electromagnetic wave. It allows only in forward direction. This is the attenuator, which suppresses the energy of the electromagnetic wave. This is the frequency. What is the frequencies emitted by the Klystron source? This is the source for the microwave that can be detected. This is the slotted section. This is connected to the amplifier, connected to voltmeter. This is the bed. Suppose I want to use the liquid here. The liquid you have to take in a particular column. Vary the thickness of the column. There is a one screw will be there. By rotating the screw, this particular flange is moving low direction to the higher. It moving from this level to the this particular level. You have to vary the thickness of the sample. We'll get the data. This microwave bend is designed only for one frequency. It works only for one frequency. You have to vary the thickness, measure the data. So as the distance is varied, you will get the data like this. Benzene is a non-polar. Benzene is a non-polar. It does not absorb energy. You will get like this. You calculate the difference between this point to this point. You will get the wavelength lambda g by 2, lambda d by 2. So you can get this. Suppose if you put the water, this technique we cannot use it for the water. It works only for low loss samples. I repeat once again, it is works only for low loss samples. This is the curve. Based on this, there is attenuation of the signal. There is a phase shift. You will get the phase shift and attenuation. From that, you can calculate the complex permittivity at that frequency. So look at this animation. This is electromagnetic wave which I'm sending to the medium. So it is a non-polar medium, so that there is a phase change. That means the beta depends upon these other parameters. This is the guided wavelength. Whereas if the electromagnetic wave is propagating through the water medium, there is attenuation of that. There is attenuation. Why it is attenuation? Because the field inside the material is greater than the applied field. It takes certain amount of energy. So that is responsible for this. So this is the setup we are using in the engineering colleges. We are using this setup for the engineering colleges. The major here it is, we have to take more amount of the sample. This cylinder height around maybe around 200 centimeters. The volume will be more. You have to take 200 ml of the sample for this technique. 200 ml, which is, suppose I want to go for a blood. I cannot take the blood measurement for 200. No one will give the 200 ml of blood. That's a major disadvantage. The advantage is this, you can measure the power handling capacity. That means you want more power through the material. This is only the method. You want to go for more microwave energy to propagate it through the medium. So you require this particular source only. Why? Because this is the vacuum tube diode or magnetron. It delivers more power. The one more disadvantage here it is. Suppose your chemical is reacting with the metal, the color is going to be changes. Once there is a change of color, you will not get the perfect value for that electric permittivity of that sample. So this method is not suitable for the materials which reacting with the metal surfaces. We cannot use it. This method is only used for the materials which does not reacting with the content. So here the practical difference is you have to sit for 3 hours to measure the one liquid sample. I'm showing at least there are 20 samples are there. This is the work I have done in my PhD. I have to sit here from morning 9 o'clock to the day after tomorrow 9 o'clock. I'll tell the difficulties. The difficulty level 1. Once the machine is on, you have to continue the range. If suppose any power fluctuations, this magnetron may give the power to the power changes. There is a source also disturbed. Due to that, you may not get the same frequency with the first point. The second point, you have to keep on continuously. You have to take the values, then plot it. When I'm measuring this, I have to sit 24 hours continuously to do this measurement for that particular composition. There is a facility to vary the temperature. So once you have done the temperature, increase the temperature and measure it. Like this, one sample, 5 temperatures. The 20 samples into 500 measurements. Each measurement will take half an hour. You can calculate how much time it will take. This is the way I have done my PhD in the last 2001 and this. Nowadays, I can do this all the sample within fraction of 10 minutes. I can complete with the temperature. So this is the beauty of the. We have different frequencies. from J band, X band, P band, and Q band. Hello. Hello. Mallikarjun, hello. There is a stuck. There is a stuck. Maybe next week. Please check on. No, it is okay. Fine. It's working fine. Okay. Okay, fine. No problem. Just wait. 1 second, same problem. Can you make full screen? No, I'm not getting the screen here. Please, please. Yeah, fine. Fine. Okay, fine. So this is a different frequency. Yeah, fine. So there is a different methods we can use it. Suppose they want to measure the solid samples. You have to take the 3 samples with the different thicknesses. You have to take the 3 different samples to measure it. Why we are taking 3 different samples? Because as thickness changes, without air medium, without sample, this is the graph. With the sample, there is a shift. Look at this sample, there is a shift. Based on this shift, we are able to calculate the dielectric constant using the transmission line method. So initially, this is the liquid setup I have used. I want to use a solid setup. I have to remove this connection. I have to insert this one into the category. I have to remove this complete part. I have to insert this waveguide into this connection. So I have to measure it. This is a long time. It takes longer time to do this. So in a colleges, especially for MSc students, we are using this one Hippel method to calculate the dielectric constant. Suppose you want to measure the liquid samples, we are using plunger method. These are the parameters. If anyone have the doubts regarding the calculations, you can call me or you can contact me. I'll give the calculation method how to do this. These are the advantages and disadvantages. I'll find there is a more time taking process and some of the samples are reacting. You have to spend 2 days continuously to measure it. I don't prefer this. The technology changed now. This is a very good method. This is set to cavity perturbation. The meaning of cavity is it stores the electromagnetic energy. Suppose the room is also cavity which our electromagnetic energy is stored. Once electromagnetic is stored means it is associated with the quality factor. So this is the cavity, rectangular cavity, where the electromagnet is stored. This electromagnetic energy is having some frequency. So this is set to the cavity frequency. This is set to the cavity frequency. If I made a small hole in the cavity, the electromagnetic wave get disturbed. That disturbance is set to the perturbation. Suppose when you are in serious mode, someone disturbed, you are irritated, right? That means that tentative moodness is changed. The same way in the cavity also, there is a disturbance. That disturbance is set to the perturbation. So without keeping any sample, this red line shows the resonant frequency of this particular cavity. Something is disturbed. Suppose inserted any material in this particular hole, it gets disturbed. This change in frequency, what is the change in frequency? That gives the dielectric permittivity. So there is a change of frequency that changes the permittivity. So based on this mechanism, you can calculate the dielectric constant of the solid samples or liquid samples, ferrite samples, polymer samples, anything. But it is only for one frequency. I repeat, it is only for one frequency region. So we have to design the cavity. Those are good at electromagnetic waves. Look at this particular equation, but design in the cavity mode. So here I'm demonstrating the cavity perturbation technique. In the rectangular waveguides, there is the dominant mode is TE waves, TE10 mode. This is set to the transverse electromagnetic wave. So this is the view of the electric field in the electromagnetic. This is the rectangular waveguide. This is the electrical field is maximum at the center. Where the electric field is maximum at the center, I made a small hole. By making a small hole, there is not get disturbed. This is a vector network analyzer. This is a screen which shows the frequency. Look at, please try to observe this. This is the cavity frequency. The cavity is resonating at one frequency. Now I'm introducing the solid. What happens? The frequency gets changed. This change in frequency, you have to calculate the dielectric permittivity. Now for liquid samples, what I'm doing now, there is a cavity frequency, this one. I'm taking the capillary tube where I'm setting the liquid. I repeat, those are doing the polymer samples or ferrite sample, they're using this methodology. Inserting this particular sample, there is a change. By this method, you can calculate. Now, I'm doing for liquid samples. In the liquid sample, I'm inserting liquid in the capillary tube. What happens? It gets changed. So due to this, we can find the dielectric constant permittivity of the liquid sample or solid samples. Now, one point is, if the liquid is more lossy, this height, look at this and this is no loss in the material. There is a loss in the material. When the height is increasing, that means the liquid is more loss. For water, this is the phase. You want to measure the dielectric constant of water, we can't measure it by using this method. This method is work for ferrite samples and polymer samples, some of the medium low loss samples. So this is the formulas for the measurement of dielectric constant. So if you have any doubts, refer to my professor literature, you'll get the complete idea about this. The next part is, these are the cavities I designed for different frequency regions. I want to measure at J-band, only have to use this. Suppose I want to design for 6.5, I have to change the length. The design of the cavity is very much important here. It takes tedious process. The design of the cavity is more tedious process by using this method. The next method is very simple method, but costly. Very simple. You can measure for solid sample, liquid sample from which frequency, zero frequency to the 300 gigahertz region at a time. More number of data points you will get better result. The problem is, this is so costly. So only certain centers only, they're using this particular setup, especially Hyderabad Central University, IIT Kharagpur, and Nanded, Swami Mahananda Marathwada University, Ramakrishna Marathwada University. Only certain places only this type of facility is there. They may use frequency domain, they may be use the time domain. The simple technique is, we're passing the electromagnetic waves from the coaxial probe. The electromagnetic wave propagating to the liquid medium. Some part is transmitted, some part is reflected. So based on the reflected data, you'll get the impedance. Once you get the impedance, you'll get the reflection. From the reflection, you'll get the complex permittivity for different frequencies at different temperatures. One single shot, once you give the power on, select the frequency, select it, it gives a wide range from 20 hertz to the 300 gigahertz. You'll get maybe 10,000 data points. If you interpret it, you'll get very good results. So this is a sophisticated method. This instrument costs around 1.2 crores. This wide setup itself 10 lakhs. So based on the purpose, which frequency range you want, the cable dimensions also will change. So there is a facilities available at University of Hyderabad. You can use it. Those are interested. So this is set with the broadband dielectric spectroscopy. Principle is very simple. We are transmitting the electromagnetic wave through the coaxial cable. Energy is transmitted through the material. Some part of the energy is reflected. Based on the reflected, we'll get the scattering parameters. From that scattering parameters, you'll get the reflection coefficient, voltage standing wave ratio. From that, you'll get the impedance. From that impedance, you'll get the dielectric permittivity. A simple case. I'll demonstrate by using this animation. This is a vector network analyzer. This is set to the Smith chart. Those are good at electromagnetic waves. They know about the Smith chart. This circle lines indicates resistance. This top line indicates inductance, the down lines indicates the capacitance. This is a resistance circle. Suppose any point is there here. This is the port 1, this is the port 2. I'm connecting to the probe, which is in the open mode. You'll get some point here. This is a sample cell. It is an air medium. Energy is transmitted, get reflected. I'm measuring the S22 reflection coefficient. I'll get the data point. This data point shows inductance, resistance. This cross point will show the R plus JX. X nothing but inductance. Suppose I'm putting a liquid. What happens? There is change in the properties. You get this. That will be the impedance. From that impedance, you can calculate the permittivity. I want to keep another liquid. I may get the point here. So it keeps on changes. So based on this data, you can get number of points. You can calculate the permittivity. Now, one more point is whenever you're measuring the permittive measurements, you have to calibrate the instrument. This calibration involves number of steps: open mode, short mode. You have to keep the reference liquid. This instrument is giving the correct value or not. Then you have to keep our unknown sample. So this is the methodology. We can use it to configure to understand the cohesive probe model. Finally, I'm trying to explain that the impedance depends upon the two factors. One is fringe capacitance. One is capacitance of the material. The capacitance you are getting in a network analyzer, there are two types of capacitance. The capacitance is associated with the dielectric permittivity. There are two capacitance, CF and C. C is for material capacitance. CF is for fringe field capacitance. What do you mean by fringe field? I'll explain here. We don't want fringe field capacitance. We require only the material capacitance. The field, this is set up the fringe field capacitance. This should be corrected. This should be corrected. We need only the material capacitance. This fringe field capacitance can be avoided. So we need only the material capacitance. This is a calibration procedure. This dielectric permittivity depends upon the impedance associated with the liquid samples. Delta 1 to delta, these are the correction factors. Just now I explained that you have to calibrate the instrument and you have to make corrections for that. Finally, we need only the material dielectric permittivity. So this method can be used for solid samples, liquid samples, solids, semi-solids, liquid crystals, anything. Suppose you want to use the sample. This is the holder for that. This is the sample. Press it long. It is stick to this. There is no air gap between the sample and the holder. Energy is transmitted. It gets reflected. It gives the data. This is one. Suppose I want to go for liquid samples. I have to dip this probe into the liquid medium. So I'll get the data. This is the different ways you can go for sample. It may be solid, it may be the granular solid. If your material is a porous, if the material is a porous, nothing but there is any air gaps is there. So you may not get the spectra properly. I repeat, if your material is a porous material, it may be the air gap is there, it's not properly packed, then you may get the disturbance in the data. If your metal is completely packed and dense, at that moment you'll get the complete reflection, you'll get proper data. Similarly, in the case of liquid also, suppose when you're doing the polymer samples or what we call is clay particles. In the clay particles, these clay particles also the responding with respect to the frequency. Up to certain frequency, the reading is going to be very smooth. After certain frequency, what happens? The clay particle, the electrons which are there in the clay particles will come out. They may produce as ionic conductivity. So at that point, you'll get reflection is going to be very high. So that is also we can already reported. So these are the different probes. We can use it for this particular method. It's very less time. One day you can finish n number of samples. With the temperature variation, it may be work for all the materials. Solids, liquids, semi-solids, one shot will get all this. This is for, I want to go for higher temperatures, I have to use this. Suppose I want to go for a low temperature region, I have to use this. Suppose I want to go for maybe a 67 gigahertz region. As the frequency changes, the dimensions of the cable also changes. So this complete cost, the toolkit is around 10 lakhs, maybe around 11.5 lakhs, supplied by the Keysight people. They have all the facilities. These facilities are available in the University of Hyderabad. The person, the researchers who are working in this field, you can use this facility. So this is about the technique. The advantages, it's a non-destructive. Means without destructing the material, you can measure. If you want to measure the blood sample, you want to measure for any proteins or anything, you can use it. The disadvantage is we can't operate for high ranges, high power ranges. The cost of the instrument is so high, is more sensitive. If a small change, it will reflect the data. So it's more sensitive. That is the reason you have to calibrate the instrument properly while doing the measurement. Once you calibrate, you can go for n number of samples. Suppose when you're doing a measurement, you got some value. After 1 hour, you want to carry out. At that time, keep any reference data what you know. Suppose you want to measure the water value is 81. So keep it, remove the sample, you have the doubt, keep it water. If you get 81, yes, correct. If not, once again you have to calibrate. For every measurement, you have to calibrate. The calibration is more important in this method. I have compared the three methods. Less than wave guide method cap is 2%. Compared to these two methods, the coaxial probe method, the percentage error is 3% because it's the most sophisticated, you get the proper value. I have done both for solid samples and liquid samples. Waveguide method takes longer time. It may take 1 day. Captive penetration may be 1 hour. Coaxial probe is only 10 minutes. So this is the time frame zone. We can measure the dielectric permittivity for this. The probe method works for all the frequencies, whereas these two methods works only for discrete frequencies. Suppose you want to specific range, you have to go for this. You can do this measurement in your engineering colleges. I think you may have the facility for the, especially for the EC engineering people, they may have the facility. They'll do the X-band characterization in the third semester. You can use that particular microwave bench to measure the dielectric constant of the solid samples or liquid samples. This is the laws. Relaxation. Once you get the data, we can use Havlicek-Negami relation. By using this relation mechanism, we can calculate the relaxation time of the solid materials, liquids, how they're responding with respect to this. This is a complete semicircle. The radius lies only along the x-axis. So by using this formula, you can calculate. This is work for water. This is a Cole-Davidson. This is suppressed semicircle. So by using this particular mechanism, in the Cole-Curl plot, beta is equal to 1, alpha varying from 0 to 1, you will get this particular graph. The second part is the Cole-Davidson. This is works for polymer samples, because for polymer sample, they have the different relaxation at a higher frequency, they have different relaxation mechanism. They can use this Cole-Davidson plot. For any clarity about this graph, you can contact me. I'll be the proper one. Fitting is very difficult. I used to do with the manually. Once it may take 1 hour to do the one calculation at a time. But if you write a program in origin by varying this particular equation, you can fit the data. You may get maybe around 10,000 points. Depends upon use. I used to select only 1,000 points in the region from 20 megahertz region to the 20 gigahertz. I'll get 1,000 points. I have to fit the graph based on the fitting parameters I used to calculate. That the instrument also provide a software which is the programmed one. Once it will give the data, it generates the relaxation time, it will give the frequency. And what's the relaxation time with respect to the temperature? One shot will get all the parameters. But the analyzing the relaxation time is a very much crucial. If you analyze it properly, you'll get the best results. So I'm interested about only in the biological system point of view. I'm looking about amino acids and proteins. I'm looking at proteins. Works on completely protein molecules, amino acids. Here I want to show that where this microwave is important, especially for the breast cancer. The use is microwave only. What is the thing here? It is there is a biosensor. This is a biosensor. There is a tissue is there. We are passing electromagnetic wave. When we are comparing the properties of the permittivity with respect to the healthy tissue and the diseased tissue. By using this mechanism, the electromagnetic wave is propagating through the body. The tissue which affected, it absorbs more energy compared to the healthy tissue. So based on this approach, we can identify what depth it is, what is the how much is damaged, what is the healthiness of the tissue that can be measured. So this type of biosensor can be used for to detect the sugar level, to detect any protein type of things. Now especially we are looking on this particular applications of dielectric spectroscopy. So this is the way I'm trying to insert a different relaxation mechanism that different frequency region, especially for those who are interested to work in the biological point of view. They have different relaxation mechanisms at different frequency region. Especially for the beta relaxation is very much important. Beta relaxation, which occurs in the low frequency region, and gamma is at high frequency region, delta is at the in between. So if you analyze this relaxation mechanism can be analyzed by theoretically or experimentally and going to work with each other. So these are the parameters. Using the dielectric parameters, these many parameters you may get with respect to the liquid sample. With respect to the solid, you may get some other parameters. We can get the thermodynamic parameters, you can calculate the expansion coefficient, you may calculate how the dipoles get oriented. With respect to the theoretical knowledge, how many number of hydrogen bonds are there within the volume, what are the bond participations, dissipation factor, all these parameters can be get with respect to this data. I'm coming to the summary. We'll discuss about the fundamentals of materials, what are the different methods. The open-ended coaxial is the best method for any type of samples, which is highly sophisticated, more sensitive data we get, and we know about how to calculate the relaxation time. If you have any doubts calculating relaxation time, you can contact me at any time through my email. I'll give the how to calculate the relaxation time mechanism in detail by taking one of the example. I'll explain to you. My interested area is only with respect to the biological samples area. I want to develop a biosensor, so which can use it for our application point of view. These are my recent publications. My research scholar Manjula and Aishwarya and Vamshi Prasad, they're working with me. So these are recent publications in the different journals. Still, we communicated 2 more papers. These are the references for this particular lecture. I preferred Kittel book and Microphysics by Samuel Diabo. So the opportunity given to the management of Vignan Institute, conveners, management, especially for Mallikarjun. I'm thankful to my Professor B.R.K. Murthy and Professor V. Subramanian. So the given opportunity to work with him for 4-5 years. Still, I'm continuing the work in the same laboratory. This IIT Madras is the best laboratory for material characterization in the respect of dielectric materials. This is the top laboratory in India. All the samples they get from that only. And one more, Professor K.C. James Ravi, senior. He's also working with the University of Hyderabad. He's a head in charge for this laboratory center, University of Hyderabad. Thank you. If you have any queries, you can contact me at any time. Okay, I'm hand over to the conveners. Any questions you can ask me now.
Yes. Any questions from the participants?
Please, if you have any questions, you can ask me now. Otherwise, if you don't have the time, just post them. Just drop a mail to me so that I can respond. My number is.
What are the applications of high dielectric constant materials?
Especially for the batteries, they're looking for that. They need a high dielectric constant means you will get a more storage of energy. Because the different frequency ranges are required. Suppose I want shielding, EMI. I need more dielectric loss. So So I have to choose different polymer composites in the material. I have to take the material, I have to take ferrite or polymer zinc ferrites. So I have to tune the properties so that I can use it for high loss materials, low loss materials. It depends upon the purpose they can use. Because the manufacturer knows that, okay, I need this much radiation is coming. So especially for the microwave door, they're coated with the EMI shielding. So this is not my energy. So I have to protect it. So go for manufacturing. So like different compositions we have to add. So to observe that. Related to the application oriented, only we are designing. Okay, fine.
Thank you.
So you mentioned in
Yes, sir. Yes, sir. Yes,
you
sir, go
mentioned in expand bench klystron is used to
Yes,
produce
yes.
like that. How the high frequency up to 30 gigahertz or terahertz?
Yeah, fine. So very good, sir. These are called solid state devices, gun diode. Especially for the vector network analyzer, we are using solid state devices, gun diode, trapez diode, impact diode. These are all the diodes. The negative resistant devices, which acts like oscillators, which can produce a frequency. And there's a limit for that because we cannot operate for higher temperatures. That is the reason this network analyzer is going to be so costly. The klystron cost around maybe the total setup may be around 60,000. The same setup for the vector network analyzer, it may cost of crores. That consists from low frequency to the high frequency. There is a crystal oscillator, especially for solid state devices they are using. For microwave oven, they are using magnetron, which is a fixed one.
Okay.
Any other questions? Okay, sir, I hope we will end the session.
Okay, thank you, ma'am. Thanks for giving the opportunity.
So much, sir. Sir, thank you so much, sir, for your participation, and thank you so much to be as a guest for us. And you covered all the important points and given a very good information. Thank you, sir. And you have spent a valuable time at this pandemic situation. Thank you, sir, once again.
I request the participants, 1 minute, ma'am. I request the participants, most of the faculty members in the colleges. So my intention is try to inspire the students towards the science. Try to do a small experiments in the classroom, like using microwave oven. Take the cell phone, take the 2 cell phone from the student, keep a popcorn. See that when the mobile phone is on, it starts dancing. It can create more interest towards the science. Okay. One more point is take the cylinder, take a tiffin box, keep your mobile phone inside, ask to call. So what is happening in that? These are all related to the fundamental science. I request all the faculty members try to do some more experiments in the classroom so that we can attract the student towards the science. We can get more innovation for the nation.
Thank you, sir.
Okay.
I thank once again all the participants to be the part of this webinar. Thank you so much for all the participants. And you will be receiving a feedback form in the list box or another banner.
Okay, fine.
You can submit your feedback form. As soon as you submit your feedback form, you all will receive the certificates.
Okay.
Ma'am, here chat box is not visible.
Chat box is not visible. Otherwise, okay, sir. We will send in group, sir. Yes.
Yeah, thank you. Thank you very much.
Okay.
Participants, if we
Okay, sir. Thank you.
Thanks. Thank you all once again.
98480.
Yes.
Madam, please repeat the mobile number. Yeah. 81897. Sir, please provide the recording. If possible, please provide the recording.
Mallikarjun, yeah, I'll
sir,
send my file to the participants so that
I say something, I will listen.
I'll provide the PDF format of the presentation. If you have any queries related to this, please, they can contact me at any time. I'll provide my WhatsApp number as well as my email ID. You can drop the mail. I'll query that. If you have any doubts, you can contact me at any time. Okay? Okay, right. Otherwise, just type my name in the YouTube. You'll get message. I will also upload in the YouTube.
Fine, sir. Thank you, sir.
Okay. Thank you, ma'am. Thank you. Mallikarjun, thank you. Class, one more class is there at 1 o'clock. Okay, fine. Okay, thank you, ma'am. Thank you, ma'am. Thank you.
Thank you.
Okay, thank you. Okay, thank you.
Madam, where
Yes,
I'll
madam.
get feedback from?
I'm sorry, madam.
And feedback from?
Feedback form.
Yeah. Okay, thank you, sir. Sir, actually, I am not in any group. If, if you send, okay, sir. Thank you.